Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the 22nd lecture of VLSI Interconnects course. We are currently in the third module of this course where we are discussing additional effects in interconnects, and today we will start our discussion on power dissipation due to interconnects. So far in this module, we have seen skin effect in the previous three lectures. So we saw the origin of skin effect, then we saw the effective resistance at high frequencies which comes because of the skin effect. And in the previous lecture, we saw an example of an equivalent circuit which would incorporate the skin effects. In this lecture, we will be starting with the discussion on power dissipation effects in interconnects. So today we will discuss power dissipation due to interconnects. So let us. So the title of this lecture is power dissipation due to interconnects. I am emphasizing due to interconnects because all the power dissipation that we will discuss in this lecture and the next lecture will not necessarily be in the interconnect. It will be in the interconnect and also in the adjacent devices due to the presence of this interconnect. So how that works we will discuss in this lecture. The reference for this lecture is broadly these two papers. However, the content is not arranged in the exactly the same way it is given in these papers, but these are the two primary references. There are other references as well. So one of the references is power optimal repeater insertion methodology for global interconnects in nanometer design. This is from 2002, published in IEEE Transactions on Electron Devices, and the other second paper is from 2004, published in IEEE Transactions on VLSI systems. From 2004, the name of the paper is Power Characteristics of Inductive Interconnect. So we will later on in this lecture and in the subsequent lecture, we will be referring to some of the final results of this paper as well. This paper is again by the Professor A.B.G. Friedman. So the problem which we are discussing is the following. There is a driver circuit here, and then there is some load, and there is an RLC interconnect. This is inductive, and as we discuss, we will see that why the introduction of inductance brings in more complications which would not have been so prominent in a simple LC interconnect. So that's why even in this title inductive interconnect is prominently mentioned. So this is our system. So you have a driver, this will have some resistance RD, and then there will be some gate here, and this will have some load. For this, what will be the power dissipation and how this presence of interconnect will affect that power dissipation we will discuss. Before we go into the breakdown of different power dissipations, let us see what are the major contributions of power dissipation in VLSI circuits. There are three major contributions: dynamic power, short circuit power and static power. So the dynamic power and short circuit power is called the transient power dissipation. This occurs when a device is being turned on and off. And then there is a static power dissipation. This is mostly because of leakage. Currents in. So this is like the static. However, these two powers, power dynamic and short circuit, are because of the transient or because of the on off nature of your circuit. So, we will label this dynamic power as P d, the short circuit power as P S c, and this as P static. So, of these three, the dynamic power and short circuit power are dependent on interconnects. These two depend on interconnect. However, static power does not predominantly depend on the interconnect parameters. So, that is the leakage current that flows through the device. So, this we will not discuss in this and the subsequent lecture. So, now let us understand what these powers are, dynamic power and short circuit power, and let us see how the interconnect is going to impact these power dissipations. So, so dynamic power, or this is also called switching power. So, is you can understand it like this. So, you have a circuit like this, there is a driver, this is R d, and there is some load capacitance C L. So, if when you give an input signal like this here, here your output would be going something like this, right. So, what is happening is there is capacitance, there is C into L, and there is interconnect capacitance. So, interconnect capacitance in this case would be C into L, the net capacitance. Now, when you charge this interconnect and the load capacitance to a voltage of say VDD, some energy is stored in your circuit. While storing that energy, some energy is also spent, which is dissipated through resistance, and because of that there is some power loss. So, basically the energy spent in making a transition of 0 to VDD at the far end of the interconnect is given by E is equal to C total into VDD square. C total is the net total capacitance. So, C total is the net capacitance. Now, this energy, so if you look at what is the expression for energy stored, it is half CV square. However, the energy spent is equal to CV square. So, in most of the references, if you read research papers on power dissipation issues, you will find an expression like this, where there is VDD square into C1. However, in one or two references, you will also find a factor of 1 by 2. So, irrespective of that, the argument which we are going to make will remain the same. However, to be more accurate, I will be referring to the paper where the term does not have a 1 by 2 factor, because see, when you are charging a capacitor through a resistor, some power is also dissipated in the resistor. So, and that then we can see that that comes out to be equal to half CV square as well. And once you have stored that power in your capacitor, when you turn off the device, that stored power is not going back to your source. So, that is also dissipated. So, in one cycle of on to off to on and then going back to off, your total energy which is wasted is C total into VDD square, where C total is equal to the inductive capacitance. So, sorry, the interconnect capacitance. So, C interconnect plus the C load. And what is your C interconnect? C interconnect is C into L. So, this is your C interconnect. right. If T is the, so this is like the energy, right, we need to know what is the power dissipation. So, if T is the time period of the clock, then energy dissipated in each cycle will be equal to this. So, energy dissipated will be C total into V dd square. Now, this power is dissipated in one cycle, right. So, your clock is you have something like this. So, you have right. So, this is your T. In this time, what is the energy lost? This is the energy loss. So, this will result in the dynamic power dissipation. So, PD would be, what is your energy lost? The power would be C total into V dd square divided by T, right, and your frequency, clock frequency, or let me write it here, clock frequency is equal to 1 by T. So, you can write this clock frequency f. So, your total dynamic power dissipation would be C total into V dd square into f, where f is the clock frequency. However, in general, a device might not be switched on and off in every cycle. There might be time where your device is not switching. So, therefore, to incorporate that, a new factor of alpha s is brought in. Alpha s is the switching probability. So, it is between say 0 or 1, 0 to 1. So, if alpha is the switching probability, the probability with which a device is going to turn on and off, then the power, the net power, dynamic power dissipation would have a factor of alpha s in the expression. So, your P dissipation would be this. So, here you can see, I mean, if you overclock your CPU, or if you are doing some high processing, this alpha s, like the switching probability goes up. I mean, more devices are used in the computation, and therefore, they are switching on and off very fast, and therefore, you will see that your laptop or your even mobile or CPU heats up. That is because when processing is more, your alpha s goes up, and then you are able to compute more, but your power dissipation is also more. Now, how will this power dissipation depend on the interconnect? So, this relationship should be simple. So, your C total comes as a linear term with power dissipation. And now, if I look at interconnect, what is my total capacitance? That is the load capacitance plus C into L, where my L is the length of this interconnect and W is the width, right. So, for this, if I take a simple expression of like parallel plate approximation, my C is equal to epsilon naught epsilon r W by d. C is per unit length, right. So, here, right, so this is per unit length, right. So, for parallel plate approximation, your C will be this, and then your C total would come out to be an expression like this. right. So now if I substitute it there, I mean in back substitute it, what I can easily get is that my P dynamic is equal to alpha into, or alpha s into C total into VDD square into F. So my C total is CL plus epsilon naught epsilon r L divided by D into W into V dd square into F. So, if I now look at this dependence, what I will get is, if my interconnect width is W, my dynamic power increases linearly with my width. So, what this tells is that my dynamic power increases as I increase the interconnect width. So, to reduce the interconnect the power dissipation, what I should be doing? I should be reducing the width. So, if I just look at the dynamic power dissipation, I get a result that okay, I need as thin the interconnect as possible. And if I just look at the RC model, in a simple RC interconnect, my R into C would more or less be independent of width. If I am taking a parallel plate approximation, then R into C becomes independent of width, because as I reduce my width, my capacitance is going to reduce. However, my resistance is also going to increase. So, my delay would more or less remain same. However, the dynamic power is not the only power that is dissipated in your circuit. There is another transient power, that is the short circuit power. So, let us see how this short circuit power would behave under or because of this interconnect. So, now short circuit power is not dissipated in the interconnect. So, in dynamic power, there was a component of power which was stored in the in the capacitance of your interconnect, and the resistance was also contributing to that charging, and so that's why that delay, I mean this power dissipation was there in the interconnect as well. However, if I look at short circuit power, it is mostly in your load device. So, what is short circuit power? So you have this VDD. Now, when you are turning this device or off to on or on to off, in that transient state, in that case, there is some leakage, some current that flows through this. This is not leakage current, this is in that on to off transition, there is some current flowing through this. So, this is transition state, and because of that there is some power loss here. So, what happens is that here you are giving some input signal like this. Now, at the output of this, so V in 2 is the output of your interconnect. So, this is V in 2 and this is V in 1. So, V in 2 is the output. Here your voltage will be going something like this. Even if this interconnect was not there, still turning on and off this device will take some time, and there would be some transition state where there would be some current flowing through this ID, and then that would contribute to the loss. However, because of the presence of this interconnect, on top of what lag there might have been here in turning this on and off, there is an additional delay because of the interconnect. So, in this state, even I mean the V into itself is not ideal now. So, when there is this transition, there would be a state where both these devices are not in, say, on or off discrete states, and there would be current flowing. So, this short circuit power, even though this does not have occur in the interconnects, this does not occur in interconnects, but still interconnect affects it. So, still is affected by. So, how does that dependence come? Let us go into a bit more detail. So, here I am showing you two scenarios. So, your V into is the output of your interconnect, right. So, this is output of connect in both these things, and V out 2 here, V out 2 is the output of your final this device. So, in an ideal case, what would have happened? Your interconnect output is like turned from 0 to 1. Once when it turns from 0 to 1, your V out, I mean if you are just looking at a digital type of thing, this would be just this an inverter. So, this would be going from high to low. In this case, the current flowing through this would not be there. So, we are assuming 0 transition time. So, you would be getting an ID as 0. Your ID would remain as 0. So, in this case, ideally there would not be any power dissipation. However, in practice what happens is the following: your V into itself is not going in a transitioning in an ideal way. So, there is some time here, transition time TR. This transition time would be directly related to the rise time and would be proportional to your interconnect delay. So, when your input is somewhere in this state, in this TR state, for this TR time, in that case what would happen is this device is not so this is not short circuited, and this is also not completely open circuited. So, there is something in between, and that is when current ID would flow through them. So, if I look at the how the current would flow, so we can assume that's okay. At this starting point, my my V into is starting to affect my load device. So, at that point, your V into would be changing. So, in that case, some current is going to flow. Before that, the current was say 0. So, and then there would be this current, and then finally, when this has reached on the final state, this has also transitioned, your V out 2 is 0, this has reached a steady state. In that case, again your current will be 0. So, in between there will be current going like this, where there will be some peak current ID peak, right, or I peak. I am writing I peak here. So, in this case there would be this current flowing through it, through this. So, your ID would be something like this. This is with time. It will be on for a period of TR, and VDD is the voltage. So, if I look at power dissipation because of this, it will be IDD into VDD into ID instantaneous. Then I will integrate it over this transition time. So, that will give me the energy dissipated in one transition. And then again, like the previous case, I will be multiplying this by an alpha s, which is the switching probability, and the frequency to get the average short circuit power dissipation. So, if I now look at what is the total power dissipation in my interconnect. So, this is P dynamic plus P short circuit plus P static. Static is not a factor here, I mean it is not dependent on interconnect. We have seen that my dynamic power is dependent like this, and we have seen my short circuit power is dependent like this. So, now I am referring to a paper here. This expression here is like oversimplistic. This is an oversimplistic expression to give you an idea like what all terms this will depend on. But if I refer to the paper which is like power characteristics of inductive interconnects, there you will find this equation. This is the second equation of this paper, and where it says that the short circuit power dissipation within the load gate is directly proportional to the input signal transmission time. So, this is the input signal transition time, which is the signal transition time at the far end of the interconnect line. Now, regardless of the load characteristics, so this is an oversimplistic case, I mean depending on the characteristics of your particular load device, the exact expression is going to change. But what it says is regardless of that load characteristics, PSC can be represented as some function of like the VDD, VT, CL and other things, and T naught. So, your T naught is the transition time. So, this is your what I was writing as TR, transition time. Right, and so basically short circuit power dissipation will be proportional to your transition time. So, your PSC is proportional to your TR, or you can say your PSC is also proportional to your TD, because more is a delay, more is your TR. Now, we come to the question, how does this delay depend on the interconnect width in the inductive interconnects. So, if when we are looking at purely the dynamic power, there we got that if I just go on reducing the width, my dynamic power will reduce. But now when we discuss the short circuit power, we saw that short circuit power depends on my delay or the transition time, right. So, now we need to first understand how would the interconnect width affect the delay. So, for that again we take a similar schematic. This is the width. Now, if I were to look at the effect on resistance, my resistance would be R is equal to rho divided by W into H. If I were to look at the capacitance, capacitance would be epsilon naught epsilon R W by D. Right. If I had only RC interconnect, then the delay would not matter. I mean for this parallel plate approximation, R into C would come out to be constant, and I would say that my delay is not, I can't control the short circuit power dissipation with my width. However, what we have is more complicated scenario where there is an inductance. So, from literature we can find out that the inductance is more or less constant with the width. So, here this is the width, and your effect of inductance, so L is nearly independent of width W, right. So, this is in micrometers. This figure is again from the paper Power Characteristics of Inductive Interconnects, and for different lengths. So, this is for 20 mm, 15 mm, 10 mm, 5 mm and 1 mm. This is for different lengths, So, if we see, I mean, if we are varying the width, it is not dependent very strongly on the L is not dependent strongly on the width. So, then how do we understand the impact on delay when this is also there? Now, there is an LC term also present. So, to get an exact expression, we will have to again go to the exact transfer function, from there get the exact output waveform, and from there we have to get the delay. But we need a closed form or close to or approximate closed form expressions. So, again we will go to the equivalent Elmore model for understanding how this width is going to affect. So, we will have some qualitative understanding of how width is going to affect the delay, and then therefore also the short circuit power. So, if I go back to the Elmore equivalent Elmore two pole approximation, my HS is given by this. Here my eta is related to B1 and B2, and my omega 1 is related to B2. For this, if I consider an unloaded interconnect, for unloaded interconnect, my B1 is RC L square by 2 and B2 is LC L square by 2. So, right now I am just considering this interconnect. This is again a very oversimplistic scenario, because I am not considering any load. However, the dissipation is going to be in the load. So, right, this is oversimplistic, but this will give us an idea, a starting point to understand how width is going to affect the delay, and then we will introduce the source resistance and the load capacitance and other terms. So, if I look at B1, my B1 is RC L square by 2, my B1 is independent of this does not vary with width. And if I look at my B2, I can say L is we are assuming that it is not dependent on W, or even if there is dependence, it is very weak. And then C is like the interconnect capacitance. So, you will have a factor of 2 epsilon naught epsilon r into D into W into L square. So, my B comes out to be linearly proportional to W. Why? Because my C is linearly proportional to W, and that comes from this expression, right. And once I know the dependence on B1 and a dependence of B1 and B2 on my W, I can get the dependence on eta, and from there I can make some estimates on how the width is going to affect my delay. So, this will require a more dedicated discussion, and we will take that up in the next lecture. So, to summarize, in this lecture we saw different contributions to total power dissipation. We saw that there is a dynamic power and there is a short circuit power dissipation, both of them comprise the transient power, and this is affected by interconnect. We saw that dynamic power linearly scales with width. Next lecture we will continue with our discussion on power dissipation. We will look how the short circuit power depends on the interconnect width, and then we will see that how, very interestingly, if I want to minimize the total power dissipation, I get an optimum interconnect width. That's all for today. We will meet in the next lecture. Good day.